test, or hadn't had it on the previous review. All right, this certainly was on there. Anytime I've done kinetics, I've done these kind of problems. First of all, you should be able to tell me from the rate law expression. Don't look up here in the equation. Just from the rate law expression, you should be able to tell me what the order of each of the reactants are and what the order of the reaction is. Okay? So what's the order of A in this case? He's first order because A has a 1 here. So he's first order. Order of B, what's B? Well, he's not in the rate law expression, so he must be 0 order. If he were in there, he would be raised to the 0 power. And C is second order. Now, that makes the order of the reaction third order. Everybody agree? Because you have to add up the exponents. Got that? All right. Now, what would happen? These are just my shorthand way of saying, don't be surprised. I told you that second page on the test has a lot of those AP exam questions. They're going to, in words, say what I'm asking you to do here. What would happen if I double the concentration of A, triple the concentration of B, quadruple the concentration of C? I got to apply that to this equation, all right? And when you do, what happens? Doubling A would be 2 raised to the first power. Tripling B would be 3 raised to the 0 power because he's not there. And quadrupling C would be 4 raised to the second power. All right, now there's easy, dumb mistakes involved. I just made one the last period. Okay, let's not make a dumb mistake here. What's 4 squared? 16 times 2 is? All right. This one, unfortunately, if you do make a dumb mistake, there's no partial credit on this. I mean, I'm not asking you to show me this work here. I am asking you to show me the work when you do with these so I can see where you made a dumb mistake. But these aren't worth as many points as these, so it's just either right or wrong. All right, this guy right here. I take 1/4 of A. 4 times B, let's just leave him out. We know he doesn't involve. And 3 squared. Okay, so it's going to be 9 times 1/4. What's the mistake we often make here? Putting down 9 1/4. That would be a bad mistake, wouldn't it? What would the answer be? What's the real answer? 9/4. Now, it's not, well, there's actually a worse mistake. People often put down this. They'll leave it like that in the blank. That's even worse. I think some people did that on their worksheets if you got it back. What's that? Well, yeah, I mean, it's almost the same thing. It's like forgetting that you're actually multiplying by this stuff. All right, so 9/4 would be, what would be a correct answer if you wanted to put it into a fraction like that, like where you have a whole number and a fraction? 2 1/4, right? Okay. So that would be okay if you put down 2 1/4. And by the way, sometimes you kind of need to do that. In the questions on the AP, I've noticed, like, for example, if it tells you, well, the initial rate was, 0.014 molar per second, and this is what happened to it. Here's what I might ask you. Oh, wait, listen to this. Watch. A lot of people are not paying attention to this because you might see this on the multiple choice kind of questions and that thing. If this was told to you as the initial concentration, and you figured out that it's going to change by a factor of 9/4, okay, you got to apply that to that number. And it might ask you, well, so what would it might be like, 0.032, I don't know what it would be times 9/4, but you see what I'm saying? Your choices would be 0.032, 0.014, 0.0, you'd have to times it by that initial rate. You see what I'm saying? It's not just that 9/4 is your answer. 9/4 is the factor by which it will change, based on the fact that you made these changes. Okay? All right, let's look at this last one. Another mistake we see in this one. Okay, we got 1/4 times 2 squared is basically 1/4 times 4, which is not 0. Don't put 0. It's 1, right? Okay, that's a good mistake that people make all the time. 1, not 0. 0 means the reaction stops. You don't do this and the reaction stops. You do that and the reaction didn't change. That's possible. All right. Now, solve for the rate law expression given this guy right down here. I think I could probably do them on the other board better. Well, yeah, there's a little bit more room over there, so I'll do that. Just ignore this graph for right now. I'll talk about him in a second. What happens? Well, I think this is the same one I was initially talking about. Maybe it's not. No, it is. I would take trials 1 and 3. So you just tell me which 2 trials you're going to take. Trials 1 and 3. Okay? This is what you have to show me. In reality, in your head, you could do this. You could do a lot of these in your head. But I want you to write it down. You're taking trials 1 and 3, and you're going to write the rate law expression. Rate equals K, A to the X, B to the Y, c to the z. You're going to write that down, and you're going to show me your thought process in terms of changing for trials 1 and 3. What happened to the rate? Well, the rate went from 2.4 to 2.4. It didn't change. The rate was 1. Now, we know in our heads, I don't have to do the rest of this, but you better show it to me, because if you don't, I can't see it. Any little mistake at that point is going to cost you all the points. I know at this point, since he's stayed constant and he stayed constant, and this guy changed, it doesn't even matter what factor he changed by. He changed and he didn't, that he has to be zero order. But here's how I showed that. The rate law constant stays the same, because the temperature is the same. A stayed the same, raised to the x power. B went up by a factor of 1.5 to the y power. And C stayed the same, raised to the z power. So basically your equation becomes 1.5 to the y equals 1. Now the only thing you could possibly get there, 1.5 raised to the only power it could possibly be, would be 0. Okay, so y would have to be 0. Got it? Did you get that for the first one? Okay. Let's look at the next one. Are there any what 2 trials did you choose next where you're holding guys constant? Looks like here, 2 and 3. I'm holding this guy constant, holding that guy constant, and this guy goes down by 1/2. You would show the same amount of work, but I'm not going to show it because I want to save some time on the review. Goes down by 1/2. What happens to this guy? He goes down by what factor? 9.6 to 2.4. If we use that by a factor of 4, or 1/4, right? So what your equation would look like would be this. 1/2 to the, I think that guy's x, right? X power equals 1/4. What must x be? X has to be second order. Okay, so we now know he's second order, and we know this guy's 0 order. You would solve for this guy the same basic way, choosing 2 trials. In this case, you can't really find, I don't think, 2 trials where everybody's held constant, or can you? No. So what I would choose in this case, since we know B is 0 order, it won't affect us. Let's not worry about what happens to him. We know he doesn't have any effect anyway. Let's hold A constant while we're changing C. Best place to do that would probably be between, well, it doesn't really matter, between 3 and 4, all right, or between 1 and 4. But either way, you would find that this guy's tripling and this guy's tripling, and therefore Z is first order. So you now know all 3 orders. You know X is second, you know he's 0, you know he's first. You have one more thing you have to do in the test. You have to solve for K. Okay? So let's solve for K. Rate equals K. A to the, what did we say he was? Second power? I erased it. A was second. B was, I remember, 0. And C was first, right? So you know all those variables. The only thing you don't know is K, because you're going to plug in these concentrations and keep your units. The rate is changing, or not changing, we don't care about the change now, we care about the absolute value of it. 2.4 times 10 to the negative 6 molar per minute equals K times, all of these are 0.20, so 0.20 molar squared times 0.20 molar times 0.20 molar to the first power. Oh, yeah. Sure. Okay, sure. Okay, bye. All right. Now, do keep your units. I would like to see the correct units for K at the end. All right, it does matter. And I'm noticing people writing now, which means tells me something. Tells me that you did the first part, but maybe you didn't think this was important. I didn't have to do this part. This is a large part of the problem. You solve for X and Y and Z. You still have to solve for K. All right. And we got to keep our units. So I've got 2.4 times 10 to the negative 6 molar per minute equals K times, now let's see if I can do all this together in my head. 0.2 times 0.2 would be 0.04. Or I'd be just squaring him. This guy is to the 0 power, so it doesn't count. So just 0.2 times 0.2 is 0.04 times another 0.2 would 0.008. Is that right? 0.0080. Now, what will my units be? Molar squared times molar is molar cubed. I do not include him. He's to the 0 power. So it'll be 0.0080 molar cubed times K equals 2.4 times 10 to the negative 6. Got that? Okay. Again, I'm noticing a lot of you are right, which means you didn't do this part. This is This is a third of the, in this case, it's a fourth of the problem. In the other, most cases, it's going to be a third of the problem. K is going to equal those two guys divided by each other. I can't do that in my head, although I should be able to. Take this on 24 how many times? 3 times. So it's going to be something 3, but don't ask me what. But the key here is the units. It's going to be 3 times something to the 10 to the something power. All right? The key are the units, though. What are my units going to be? I'm dividing molar per minute over molar cubed. What am I going to get? Molar to the negative second, minute to the negative first. Okay? Or 1 over molar squared minutes. Either way would be correct. You see why? And your answer is 3 times 10 to the negative something. I don't know what. But it doesn't really matter. Fourth? Negative fourth? All right. Everybody good with that? All right. So, can you see, when you get this chart, it's kind of a chart, can you see how to do the exponents and then K? You think about it, in every case, we're all going back. Good question.
When we put the K into the rate law expression, then do we have to include the answer? Can we just,
well, you're just going to be solving for K. That's all. You don't have to rewrite the entire rate law expression again. The answer to this question will be, you don't have to rewrite it all at the end. Just tell me X equals this. At the end of that one, circle that answer. Y equals this, and circle that answer. At the end, K equals, circle that answer. That will be all. You don't have to plug it back in. Okay? Because those are the variables you were searching for anyway. All right, good enough. But again, like I was about to say, every one of these problems is asking you about mechanisms in a different way. Remember my little demo up here. 3 people standing here. Slow step. 1 person in the middle here. I happen to put him in the middle. Could have been the beginning or the end. All right? The slow step controlled the overall rate of the reaction. That's what these exponents mean. You can't lose sight of that. That's also what it meant when we were doing this stuff here a minute ago. Okay? These things here. What does that 2 mean up there? It means he's in the slow step twice. He's in the slow step once. He has effect on a rate by the same factor. Same factor raised to the second power. So when I double or triple. So I'm looking at it from multiple different ways. Here I'm changing concentrations given the rate law expression. Here I'm figuring out the rate law expression having changed the concentration. You see what I'm saying? We're kind of working backwards in those 2 cases. All right. Now let's look at the graphs. Let's start with this one. We'll start with this guy right here. I told you to look that up as you were doing the review. Okay? What would this have to be? The blue line. What would that have to be the graph of? Of a product. You all agree? This would have to be the graph of a product. And the reason this guy slopes the way he does, we explained that before. First of all, it's got a positive slope because the product's increasing over time. This guy would have to have been a reactant, correct? All right, how would you have to do the slope? What if I ask you, using one of these charts, what would the slope be for one of these, the red one, for the red line? What would I be for the slope there? It would have to be positive or negative. That's all I care about right now. It would be negative. Now, if I gave you the actual equation like this, okay? Say this guy was like probably something like 2A yields 4B plus C. That's probably what that would look like, right? You see why the coefficients are what they are? How would I get the actual slope that I know it's negative for this guy? It would be a negative, what? Change in y over change in x. But what would you have to do with it because of the 2? Look back at your notes right now. I told you to look back there. Right, but you should know that. All right, look back, okay? It says that. The example right after that thing, it says that you have to take into account that coefficient, which would be 1/2. You see it? There? Okay? All right. Now, what about these graphs here? They're part of the endo and exothermic ones. You should know all the parts of this. Okay? There is, one of the kind of questions I could ask you about this. Well, I could ask you questions about which one's endo or exothermic. What would you say? Endo or exothermic? Let's call this guy A and call this guy B. Which one's endo? Endo. B. He's endo. Because he's absorbing energy over time, he's gaining energy, he gains more energy than he gives off. But there is some energy given off in both cases, notice. This guy, you put a little energy in, you get a lot back. He's exothermic. Which guy is going to be more likely or favor spontaneity? We know from last chapter. exothermic. Things tend to go from high to low in general. All right? Things don't tend to go from low to high energies in general. Okay? But there are other factors. We know that from thermodynamics. There's entropy and there's temperature. All right, that will determine this. All right. What else could I ask you about this guy? Oh, I could ask you how a catalyst works. Right? How does a catalyst work based on this reaction? What is it basically doing? Is it pushing him over the hill? We always use that analogy. Is that right? You write that down, you're losing a lot of points. What is he really doing? He's finding a different pathway, a different intermediate, whatever, a lower energy way around that hill or through that hill. He doesn't need as much energy to get there. Okay? I could ask you, which would more likely be, which one's giving off energy? Yeah, overall, this guy's giving off energy, he's absorbing energy, more likely to feel warm or hot, more likely to feel cold, absorbing energy, right? All right. So those are the kind of questions you might see on those graphs. By the way, some of the other things. What do we call this value right here? Well, actually, in this case, the value would be from here to here. What do we call that value? The activation energy. What do we call this thing at the top, the highest energy point? Activated complex. All right? These are all things you have to know. It's written right on there. I know. It's kind of silly. It's not going to be on there on the test if I ask that question. All right, so there are your graphs. You're going to have questions on this graph and this graph and this graph. Guaranteed you're going to have to use those graphs somewhere. Okay, great. This is the where I give you mechanisms. Remember I told you, so far I talked about two ways. Kind of like one was forward, one was backward. This is looking at it from the inside out. Here is the mechanism. And I want you to tell me if it's consistent with the rate law expression. Okay? Now, in the previous two, I was making changes either in my experiment, like we did in the lab, and then determining the rate law expression, or I was given the rate law expression and making changes to see what would happen. Here, I'm simply asking, does this make sense? Could this be a mechanism if that's your rate law expression? What do you think for the first one? Could it be? Yes, because NO, is supposedly used twice in the slow step. You say, well, he's not used twice in the slow step. He's only used once. Actually, he's used once here in a previous fast step, and then the intermediate that he formed, this guy's an intermediate, I could ask you that, identify the intermediates, is going to make, reacting with another one of these, that's two of them. All right? So, by the way, this guy was also used in that previous fast step. How about this guy? Does that make sense? Is that consistent? Yes, it is. Okay? Because you're using two NOs and one Cl2. Two NOs and one Cl2 in the slow step. He determines the overall rate of the reaction. Is this consistent? Why not? Because the rate law expression for this guy would have had to have had NO and Cl2 to the first power. They're only used one time. See it? All right. Before I leave this board, real quick, some of those questions, a multiple choice, and on the first page, my fill-in-the-blank multiple choice will be on collision theory, transition state theory, and the four factors that affect the rate of reaction. By the way, those four factors, don't get them confused. Don't tell me I could powder them, I could increase the surface area, I could dissolve them in water. Those are all the same thing. Those are the nature of the reactants. You should have, what are the four factors? Nature of the reactants is one. Allotropes included in that. Nature of the reactants, temperature, what else? Catalyst and concentration. No, see exactly what you said. You can't say surface area, powder them, crush them, dissolve in water. They're all the same thing, changing the nature of the reactants. All right, you can't say those. Yeah.
For A.
Yeah.
Did NO and Cl2 count as step one?
Yeah, they count as
because they're before the slow
right before the slow step. Exactly. All right, and now the last one here is the one that really. I know most of you, I did try to explain it as best I could, but most of you are probably just going to have to memorize this for the test because you haven't had calculus. This one makes sense, and this one makes sense. This one's the hardest one to understand. If you graph concentration versus time, if you go back to those notes, you look at it, you will get a straight line slope, and that makes sense because the concentration doesn't have any effect. The change of concentration doesn't make any difference. That only happens probably only happens when you have a heterogeneous catalyst, like a surface area of the catalyst is determining the actual rate of the reaction. This guy's what you'll normally see in a first-order reaction. See a lot of these. We're going to see it again in decay problems, like half-life problems. When you graph the natural log of concentration versus time, you will get a straight line. That tells you that this guy was zero order, by the way, I didn't say it. This guy would be first order. And where you get this guy 1 over as a straight line, he's going to be second order for the reaction. All right? So you have to be able to identify that. That's all you'll have to do. I realize that's probably a little confusing for most of you. All right?